Hi, we're back with our second part of Lesson 1 in Kinetics. In the first part of the lesson, we looked at the idea of how to calculate the rate of a reaction, which is the change in concentration over change in time, and gave you a little introduction to how to write a rate law. In this lesson, we're going to use experimental data to write a rate law and determine the order of one or more reactants in a particular reaction. So the method we're going to use is called the method of initial rates. You don't need to know the name of it, but just know that you're going to be receiving a data table for these particular questions. So experiments are set up where each reactant's concentration varies independently of the others, and then the initial rate of the reaction is determined. And you can determine from this information the order of the reaction with respect to each of the reactants. So I'm going to show you an example in this sort of scenario. We have a reaction A plus B yields C, measured for several different starting concentrations of A and B, and we're going to give the results in the table in the next slide. So we're going to determine the rate law for the reaction. We're going to calculate the rate constant and calculate the rate of the reaction when concentration of A is 0.05 molar and B equals 0.1 molar. So this is the data table that you would be receiving for any sort of practice questions that we'd be doing. You'd be given a set of experiments, you'd be given the initial concentrations of any reactants involved, and you'd be given initial rate of the reaction. Recall from the prior lesson that a differential rate law takes the form of rate equals lowercase k, which is a rate constant, times the concentration of any reactant raised to a certain order, multiplied by the concentration of another reactant raised to another order. The rate constant has units that you will have to either memorize or derive. And it's based off the idea that rate is equal to, the unit is molarity times second to the negative first power. All right, so what we're going to do here is compare the data in these tables. So what we want to do is we want to see if we can hold one of the concentrations constant while just examining the other reactant's concentration. So if we look at reactions 1 and 3, the concentration of B stays constant, kind of as a control. So we can just examine what happens to the concentration of A and how that impacts the rate of the reaction. So you can see here that when the concentration of A is doubled, the initial rate of the reaction is multiplied by what factor? It's multiplied by a factor of 4. So based on the pattern that we examined in the last lesson, if I double a reaction and then I end up multiplying a rate by 4, that's 2 squared, that means that this particular reaction is second order with respect to reactant A. Now we're going to look and see if we can examine the data to get the order of the reaction with respect to reactant B. So we'll use the same method. We'll see if we can hold A constant and just examine a change in B. So if we look at experiments 1 and 2, the concentration of A is constant, but the concentration of B is doubled. Now, if I double the concentration of B, what happens to my initial rate of the reaction? There's no change. So based on the example that we looked at in the prior lesson, if we change the concentration of a reactant and there's no resulting change in the initial rate of that reaction, that means that that particular reactant is a zero order reactant. So we're second order in A and we're zero order in B. So we want to come up with the rate of this the rate law for this reaction. We would write down rate equals K, the rate constant, times the concentration of A raised to the second power times the concentration of B raised to the 0 power. And since you know that raising anything to the 0 power is 1, we would omit that from the final rate law, and it would just be rate equals rate constant times the concentration of A squared. If you were to then calculate the value for the rate constant, you could take any of the experiments and substitute in the values and solve in that way. So what I did is I took just experiment one's data, and I substituted it in to this rate law that I came up with. So the rate was 4 times 10 to the negative fifth. The rate constant is k, and we're going to multiply that by 0.1 squared because that's the concentration of A in experiment 1, and we're squaring it. And again, concentration of B has nothing to do with the rate law. So when you solve for k, k ends up being 0.004. Now, you need to be able to determine the unit for the rate constant. You can do that by examining the order of the reaction. The order of this reaction overall is a second order reaction. It's just the sum of any exponents, the sum of any of the orders of the reactants. So our second order reaction, you would have a unit of let me change color, molarity to the negative first, second to the negative first. The reason why this would work is based off the unit for rate and the math that we did for the rate law. So the unit for rate is molarity times seconds to the negative first power, the change in concentration per unit of time. So if our unit for K is molarity to the negative first times second to the negative first, so that's our unit for K that we just wrote down, and then we multiplied that by the concentration of A squared. The concentration of A is in molarity. If we square that, we have molarity squared. So when we put together all of these units on this side of the equation, the molarity to the negative first and the molarity to the second power even out to molarity to the first power, which is the same as it is on the rate side. And then we have the seconds to the negative first power, which is what we have on the other side as well. So you need to be able to calculate the rate constant and as well as writing the correct unit. That's always going to be part of that portion of a question. Oh, and I'm back again. I think there was a third part about asking for the rate when the concentration of A is 0.05. So we can substitute that in as well. So the rate we're trying to calculate is equal to, we have the rate constant, 0.004, times the concentration of A, which was 0.05 in that question, squared. Again, it doesn't matter what the concentration of B is. It has nothing to do with the order of the reaction. So that comes out to 1 times 10 to the negative fifth, and since we're solving for rate, it would be molarity times second to the negative first power. And we're finally done with this slide. Pinky promise. Ta-da! Okay, so now for this question, this one's spread out over a couple slides. Write the rate law, determine the value of the rate constant K, and the overall order for the following reaction. So we have 4 experiments given to us. We have 2 different reactants. We're given their concentrations, and we're given the original rates, the initial rates for these. So take a look at these 4 experiments and try to determine which experiments we could use to calculate, to write the rate law, and then in turn we'd be able to calculate the rate constant. Okay, in this particular example, we're going to look at first experiments 1 and 2. In experiments 1 and 2, we're doubling the concentration of the nitrogen monoxide while maintaining a control the concentration of chlorine. So when we look at how the rate changes in response to the change in concentration of the nitrogen monoxide, when the concentration of the nitrogen monoxide was doubled, the rate of the reaction was multiplied by 4. So that means, based on our prior pattern, that the order of the reaction with respect to the nitrogen monoxide is a second order. So we have part of our rate law written in now. For the chlorine, we can look at experiments 2 and 4, because in experiment 2 and experiment 4, the nitrogen monoxide is held constant while we're doubling the concentration of just the chlorine. And we can look to see what happens as a result. So when you double the concentration of the chlorine, you are also going to be doubling the initial rate of the reaction. So we would just take this number divided by that number, and you'd get the 2 as a result. So since there's a parallel magnification of both the concentration and the rate, it's doubled and then doubled, that means that it's first order with respect to the chlorine. So that would be your overall rate law. Now the next part of the question was to calculate the value for the rate constant by using any set of experimental data. So because it's a rate constant, K is constant for any particular temperature, you could choose any experiment and substitute in the values and you'd be able to get K. And we're going to actually do that in class. There's going to be an exercise you're going to work on where you're going to write out or calculate the rate constant for a set of experiments, and you'll see that it's the same. So for this particular slide, it was using the data from experiment 1. So all we did here was substitute in the values. It looks kind of cumbersome right now because they included all the units while the calculation was going on. And I don't typically do that just because it gets messy. I just always want to make sure I check my unit at the end. So all we did here was substitute in. So we have the rate, which is 1.43 times 10 to the negative 6th. We have the initial concentration of the nitrogen monoxide, which was 0.25. And we have to square that because we said the reaction was second order with respect to nitrogen monoxide. And then we're going to multiply it by the concentration of chlorine, and that would be raised to the first power because it's first order with respect to the chlorine. When you solve everything out algebraically, you end up with a K value of 9.15 times 10 to the negative 5th power. Now, the unit here is not how I typically write the units for my rate constants. But it's totally up to you. But to figure out the unit for the rate constant in this case, you want to look at the overall order of the reaction. So we said that it was second order with respect to nitrogen monoxide, and it's first order with respect to the chlorine. So that means that the overall order of this reaction is a third order reaction. So for the unit for K in a third order reaction, you got to think of it as adding up all the exponents should come up with the number of the overall order of the reaction. You're actually going to take the absolute value of it. So we know that seconds to the negative first power has to be a component because that is a component of rate. So what number, when I add it to -1, would give me an absolute value of a total of 3? It will be -2. So the other component of this K unit is molarity to the negative second power, which is what this is. It's just molarity flipped over, squared. Oh, and then the overall order of the reaction is third order. So again, let's just add up the exponents or orders of each of the reactants. I'm going to work through one more example with you, and it can be done without the information that's good on this slide, but I'll show you what I mean in class. So the idea here is if I have a set of experimental data and the concentration of one of my reactants doesn't remain constant, so I can't use it as a control for something, like how do you go about determining the rate law or the order of the reaction with respect to that particular reactant? So you want to solve and figure out the order of whatever you possibly can. And then what you're going to do is take any two experiments and set them up as a ratio to one another and solve algebraically. So again, the example that I'm going to show you in the next page solves it this way, even though it doesn't have to. But I will show you in class an example where you'd have to use the algebra to solve this equation. It sounds messy without seeing an example, but it's really not. Sorry, this is a little blurry for some reason. So we have 3 different experiments. We have the overall reaction, and we want to try to do the rate law, the rate constant, and the order. So just like the last example. So let's look at, first of all, can we determine the order of the reaction with respect to the nitrogen monoxide? So think about which 2 experiments you could use to just compare how the change in NO affects the rate. So to figure out the nitrogen monoxide, I'm going to use the experiment 1 and experiment 2, because in experiment 1 and 2, the concentration of the hydrogen remained constant, so I didn't have to worry about that was my control. So I'm just looking at what happened to the nitrogen monoxide. So for the nitrogen monoxide in in experiment 2, its concentration was 0.1. In experiment 1, its concentration was 0.2. So it was doubled. So what happened to my rate? My rate went from 0.0225 to 0.09. which is multiplied by a factor of 4. So for the nitrogen monoxide, when the concentration was doubled, the rate was multiplied by 4. So that pattern is follows along with a second order with respect to the nitrogen monoxide. So we have that filled in. We know it's second order. To figure out the to figure out the hydrogen, you can use experiments 2 and 3. Now it's not a whole number change. So the nitrogen monoxide is a constant. In experiment 3, it was a 0.2. In experiment 2, it was a 0.3. So the factor that we multiplied it by was 1.5. So when you look at how the rate changed, to get from 0.015 to 0.0225, that changes by a factor of 1.5 as well. So when we have them changing, the concentration and the rate changing at the same factor, then that's indicative of a first order reactant. So the math here looks really messy. The math in this example was kind of done unnecessarily, but I'll explain it in class with a better example that we can work through together. So for this particular reaction, we now have the order of each of the reactants and can determine the rate law. So our rate law, based on the experimental data that we figured out, was second order with respect to the nitrogen monoxide and first order with respect to the hydrogen. The next part of the question was you had to calculate the value of the rate constant. So the way this is set up was already rearranged. So it was just taking experimental data and substituting it in. So the rate they used was 0.09 equals K times the concentration of NO squared times the concentration of hydrogen, and that was raised to the first power. So when you solve for K in this case, it ends up being 7.5. Now the overall order of this reaction is a third order reaction. So the unit for K would have to be molarity to the second power, to the negative second power times seconds to the negative first power. The sum of those exponents in my rate constant unit adds up to, when you take the absolute value, to the overall rate order of the reaction. So that's just kind of an overview of how you can use experimental data to determine the order of a reaction with respect to each reactant, and then write the rate law and calculate the rate constant. So last question here, how do exponents or orders in rate laws compare to coefficients in balanced equations? They are unrelated. The stoichiometry of the reaction doesn't tell you anything about the order of a reaction with respect to a particular reactant. It just tells you the stoichiometric relationships between the reactants and products. It doesn't have to do with the rate. So that's something important to remember, is the coefficients in an overall reaction do not tell you anything about it, the orders. So sorry about my voice. I smoked 3 packs of cigarettes before making this video. JK, I have laryngitis. Hope you enjoyed it. Not really, but I hope it helps. And we're going to solve a bunch of these problems in class, and they're very systematic and very formulaic, so you will love them. Okay, bye.